Is it possible to make a revision lecture in an airport? This is an experiment to find out. I'm going to go over the questions from the 2018 to 2019 exam paper in order. Just general advice to all of you for the exam, which I always give to all students, is read the whole paper before you start doing the questions and tackle the questions from the one you think that's the easiest to the one you think that's the most challenging. Don't always start with the compulsory question. If you feel more comfortable doing one of the others, you get the same marks whether or not you finish the compulsory question. Just because it says compulsory doesn't mean you have to do absolutely the whole thing. So the first question, the first part of it, is all about remembering a statement of the equivalence principle. This seems like a sensible thing to do when you're revising for an exam in general relativity. So the statement of the equivalence principle is as follows. An observer in free fall in a gravitational field making local measurements gets results identical to those of a non-accelerating observer making the same measurements in a gravitational field-free region. Okay, so the next part is about the trajectory of a body which is mimicking a gravitational field-free environment for astronauts. So here you just have to remember the equivalence principle, which says that if you're in free fall, there might as well be no gravitational field. So all you need to do the problem is to realize that the aircraft has to mimic a freely falling body. Now, of course, if it just fell vertically, everybody would die. So there are other freely falling bodies which are launched at 45 degrees above the horizontal, will make a parabolic arc in the absence of air resistance. So the answer you want for this question is that the plane has to move in a parabolic arc following the constant acceleration equations with a constant acceleration directed downwards. The bit about the height of the plane being small compared to the radius of the Earth just means that you can think of the acceleration as directed vertically downwards everywhere. You don't have to account for the Earth's curvature. So you'll get full marks if you hand sketch something like this. And I'm sorry I can't do a hand sketch because I'm in an airport, so I've had to use a plot. Notice I've made use of a label to show that I understand it's a parabola, not just made a rough sketch. And also, it would do no harm to label the angle at the start with 45 degrees as well. The next part of this question, like many of my questions, its bark is worse than its bite. All you need to know for this question is your constant acceleration equations. Now, horizontally, it's not accelerating because the acceleration is directed vertically. So horizontally, if you know the initial velocity, which is just the magnitude of the velocity times the cosine of 45 degrees, or 1 over root 2, all you do for the acceleration equation, the trajectory, is write x of t equals v over the square root of 2 times t. For the vertical motion, you use the, I guess people call it the Suvat equation, s equals ut plus a half at squared, except there's an initial displacement h, which you write in, and u is your initial vertical component of velocity, which is the magnitude of v over the square root of 2 again. So it's h plus mag v times t over the square root of 2, and then minus gt squared over 2, because the acceleration is g downwards, so you get minus g. And then you have t squared over 2, and that'll get you the marks. So the algebra is shown in a minute. For the next part of this, you just need to recall the very first time we met the Christoffel symbols. And the first time we met them was in decomposing partial derivatives of basis vectors. We discovered that you can write the partial derivative of a basis vector as a superposition of the basis vectors themselves, and the coefficients of the superposition are the Christoffel symbols. So if you look at the piece of algebra coming up, you can see the result that you need to write down. Right, so for the next part, we have to start with the partial derivative of a vector. The vector I've called A with an arrow above it in the algebra that's coming up. Then you decompose A as a superposition of components A nu times basis vectors E nu. Because you're taking the partial derivative of a product, you use the product rule to decompose the derivative into two pieces. One of the pieces, the one on the left, contains the partial derivative of the components, which is the normal piece. The other one contains the partial derivative of the basis vectors. But in part C, we already know that the partial derivative of the basis vectors can be expressed as a superposition of basis vectors times Christoffel symbols, so you make that replacement. Next thing is you need to swap the indices nu and kappa in my algebra. You could have chosen something else instead of kappa. It doesn't matter what you choose as long as you're consistent. When you've swapped those indices, you can factor out the e sub nu, and the thing in the brackets is the covariant derivative big D sub mu of a super nu. So that is the definition of the covariant derivative. You can see that it is a tensor of rank 1, 1, because it's multiplied by a tensor of rank 0, 1, that is e sub nu, and the thing on the left is a tensor of rank 0, 1. So that's the solution to part D. So just to recap, the critical steps are to break the vector down into its components, then substitute in the Christoffel symbols for the derivative of the basis vectors. Finally, swap the indices in the second term. Once you swap them, you can factor out the basis vector e nu, and the thing that's left in brackets is the definition of the covariant derivative of your vector components. Right, now I'm actually on the plane. I can see if a vision lecture works when you're doing it on a plane as well. Sorry about the nerdy headphones. We're on part E now, and you have this equation, the divergence of E equals rho over epsilon 0. Now, the trick here is to write the divergence of E in terms of operators that can be converted into tensors and convert it to a tensor equation. Once it's a tensor equation, it's valid in all coordinate systems. So the trick here is to recognize that the divergence of E can be written as partial sub A E super A. Now that's not a tensor, but you can replace the partial sub A with big D sub A, and then big D sub A E super A is a tensor. You can set that equal to rho over epsilon 0, and then recast your big D sub A of E super A as the sum of partial sub A E super A and the Christoffel symbol multiplied by E super A, and that equation is then a tensor equation, valid in any coordinate system. So that'll get you all the marks for question 1. Now we go on to do question 2.